Let's talk about QuickSort. When I say QuickSort, you should think of one word: pivot. The idea behind QuickSort is we're going to take the list and pick a pivot at random. Let's say we pick 5. Alright, so we want all the elements on the left of 5 to be less than 5 and all the elements on the right of 5 to be greater than 5. That's called partitioning the list around the pivot 5. So how do we do that? Let's loop over the items. 3 should go on the left. 3 should go on the left. 6 should go on the right. 4 should go on the left. 1 should go on the left. 8 should go on the right. 7 should go on the right. 2 should go on the left. Okay, so now let's say that we could magically have the left-hand side sorted. And magically have the right-hand side sorted. Well then, everything would be sorted. So by having the pivot, we've basically simplified the problem from sort the whole list to just sort these 2 sublists, and then we'll be good. Now how do we sort the 2 sublists? Well, we use recursion. We call QuickSort on the sublist. And since the lists are getting smaller and smaller, eventually we'll get to our base case, which is if there's only 1 or 0 elements in a list, in which case it's already sorted, and we're good. So that's the idea behind QuickSort. Now let's take a look at the code. So this function will first check if a list has 0 or 1 elements, in which case this list is already sorted, so we don't need to do anything. That's the base case. So for the recursive case, we're first going to get a pivot, and we call this function to do that. And what this function does is we pass in the starting index of the list, which is 0, and the ending index, which is the length of the list. And it will give us a pivot at random inside. So it'll give us a random index. How does it do that? Well, it calls this random function. Okay, so this pivot value, we're going to have our list, and the pivot is going to be somewhere picked at random. And then our job is to construct the left and right lists such that we can have our list like this: left, P, right. That's our partition being done. So we loop over every value in the list. If it's the pivot, don't add it to left or right because this is its own category. If the value is less than the pivot, put it into the left. If it's greater than the pivot, put it into the right. All right, now we have left and right. Now we want to call sort on left and call sort on right. And then we want to combine the output. The output sorted list is going to be the sorted left, the pivot, and then the sorted right. This asterisk is the spread operator, so it just takes out all the elements so we don't have nested array. Great. So that was the easier way to do it because we didn't need to do it in place. Now let's talk about QuickSort, which is how do you do it in place, because here we were creating a copy and everything. So in place is going to be more memory efficient and performant. So with this implementation, we're going to find the pivot. Again, we have the same base case. All right, and then we're going to find the pivot. Oh, and you might notice here, we're calling it QuickSort on a list specifying a start and ending index. So this time, you give me a list and tell me, just sort this list between these indices. I don't care about the rest of the list. So that's how we're able to use just one list. So we're not copying anything. So we're going to find the pivot. All right, so if our start index is 3 and our end index is 10, then find a pivot somewhere between 3 and 10. And then we're going to call this function called partition, which is going to take in the list, the starting and ending index, and the pivot index. And partition is going to partition the list around that. So if we have our list and we have our starting index here and our ending index here, and we have our pivot index here, then it's going to take this region and it's going to pivot it correctly so that everything over here is less than p and everything here is greater than p. How does it do that? Well, this is kind of an interesting problem which I had a fun time solving. So we have to create the pivot, and I actually wrote out this process here. Here are the stages of partitioning. So first, we want to take the pivot and we want to move it to the beginning so it's out of the way. Okay, so now pivot is at the start. Then we want to take every vertex in the list and we want to incorporate it into the left or right. So what we're doing is we're growing the list. So if we have p at the start, we're growing the list so that we have a left section and a right section. And then the rest is being inserted into, so for every element v here, if it's less than p, we're going to put it here into the left section. If it's greater than p, we're going to put it into the right section. So how do we do that? So for a given element v, we're going to actually have two pointers here. We're going to have a left index and a right index. And the way it's going to work is all the elements between p and the left index are going to be part of the left. All the elements between the left index and the right index are going to be part of the right. So if the current value we're processing is supposed to belong to the right, all we have to do is increment the right index, and then it'll be included in the right. The more complicated case is, what if v should be in the left? Well, in that case, we have to do some maneuvering, because we can't just increment the left. So we have to move v over here, then increment the left, so now it's included, and then also increment the right. So that's this in action. We take v was here, now it's here, and we take the first element in the right and move it over here. And now, as you can see, this region is the right and that region is the left. And because v is less than p, this is all part of the left, and r was always r hat was always greater than p, so we have our valid right region. So this took some trial and error to come up with, but it works. You take a value, once more, if it's greater than p, you could just have the right consume it. But if it's less than p, you have to move it over here, grow the left, and then since you swapped it with an element that was in the right, it's still fine because that is in the right. Okay, so the nice thing about partitioning is you just have to do some O of one work for each v, and you're doing that over all n items. So partitioning is O of n. Oh, and the last thing you have to do is we have to move the pivot to where it belongs, which is between the left and the right. And you can do that by swapping p with the last element in the left. So that's what all the parts of this code do. We have we put the pivot at the beginning, then we have li and ri. Now originally, like, you could do li and ri and manually increment them, or you could just have a for loop take care of that for you. So ri at each step is just moving up, and then we have our element v. If v is greater than p, then it should go into ri, so ri is just going to move up one. If v is less than p, we're going to have that swapping mechanism. So li is pointing to the first element in the right, which is r caret. I did that because it's like regular expression notation, you know, first part of r. Anyway, and then ri is going to point to v. So this is saying swap Li and Ri, Li being the first element in R, and Ri being V. So that's the swap here. And then you also have to increment Li. That's what that does. And then in the last part, we're going to be moving, step 3, we're going to be moving the pivot to the end of the left in order to have our left region to the right, to the left of the pivot, and the right region to the right of the pivot, such that the right elements are greater than P and left elements are less than P. So that's partitioning. This is all in place. We don't have to make any copies of the list, which is nice. Then we are going to run QuickSort on the list on the left part. So we're going from the start index to the new pivot index, and then from the new pivot index plus 1, which is here, to the end of the list. Now you might notice there are 2 pivot indices. This was a bug I had earlier. I just had one. But you have to remember that once you pick the pivot and you partition, the pivot moved somewhere new. So you have to have that new partition pivot index be where you are doing the QuickSort from. So yeah, that's the in-place one. And here's a working implementation. All right, and now for the C++ implementation. So for the C++ implementation, it's the exact same logic except using some, C++ lingo. So main thing is you have to work with vectors, and so when you're merging lists, you have to use the vector iterators and all of that jazz. And then when you're working with partition, here it is, same logic, just in C++. Okay, let's talk about runtime. So the thing we have to keep in mind is picking the pivot is O of 1 work. All of this stuff is O of 1 work. This line, the partitioning, is O of n work. So let's say T of n is the amount of time it takes to run QuickSort on a list of size n. So we have O of 1 plus O of n for the partitioning, plus 2 recursive calls. One of them is going to be to the starting list, and the other one's going to be to the ending list. So now it depends on how we pick our pivot. If we pick the median as the pivot, then the left is going to be size n over 2 and the right's going to be size n over 2. That's the best case scenario. So let's do best case first. So this is the same as what we did with merge sort, right? It's the same equation. We have 2 times t of n over 2. So you can look at the merge sort video to see how we can transform this into t of n equals O of n log n. Now, in the worst case, the partition is going to be such that it's basically not very good. So if we pick the partition such that all the elements on the right are here and the left is empty, the partition barely helped us. So for example, if we have the elements 1, 2, 3, 4, 5, 4, and we pick the partition 1, well, then everything's going to be on the right. So then if we again pick the partition 2, then everything's going to be on the right of 2. And then if we pick the partition 3, everything's going to be the right of 3. So this means we'd have to pick the partition n times. That would be if we had the worst partition. So that means that it would be O of n squared work, because we would be running QuickSort on a list of size n, a list of size n minus 1, a list of size n minus 2, etc. So we're running QuickSort n times, and each time it has to do O of n work. So that's going to be O of n squared. Okay, so that was all theory. Let's actually plot the time complexity from running it as an experiment. And as you can see, it does appear to be O of n log n. Now you might be wondering, if we're picking a pivot at random every time, how do we know that it's going to be closer to the best case than the worst case scenario? And there's some fancy math you can do with probability to show that in expected runtime it's going to be O of n log n. So almost always you're going to be towards the O of n log n, not the O of n squared. So yeah, that's it for QuickSort.